Here the clap. Well, too late. Okay, welcome everybody. Our guest speaker today is Professor Arielle Phillips, who's an associate professor of the practice in the Department of Physics and Astronomy, and associate dean of collegiate affairs at the College of Science at the University of Notre Dame. Arielle did her BSc at McGill University in Montreal, where she's from, and she was also a CITA summer student, so she's a citizen. She did her PhD at Princeton University, and then postdocs at Caltech and Amherst College, where she was a 5-college astronomy department fellow, working on research and education, but not research in education, which was a distinction that I was made clear I should make.
Just in case anybody asks me a question about research in education, and I
very different.
Not be able to answer any questions. Yes.
So Arielle's worked on a broad range of topics in cosmology. Her research group has developed simulations that find and characterize structures in the cosmic web, and have applied them to the study of the evolution of galaxies across cosmic time. She's happy to answer questions as we go along, but reserves the right to push any to the end if they seem like they're going to take too long to answer. Let's all welcome her. Her talk today will be called Tracking the Edge, the Environmentally Dependent Evolution of Galaxies. So let's welcome her.
Thank you. It's nice to be back after, I won't say how many decades. So it's not quite, it's decades, but not maybe as many as you would think. This work that's kind of come together over time as I studied different topics, but you'll see that perhaps it was always meant to be. This is work I do with my group. We're kind of a ragtag bunch of professors in the department, including Grant Matthews, my colleague. We often share graduate students. Long Nguyen, who just joined my group as an associate research professor. Keith Davis, who's been the director of the Digital Visualization Theater, who has just joined our team, so do not attribute any of the look of our figures to him, as a kind of an information design specialist. He also has a PhD in astrophysics, but I thought, hey, let's start talking like that and then see where this conversation goes. And you'll see in a moment why I recently added him to the team, other than we also will have very soon a lot of information we'll need to share with our field. A couple of off-site people, including Inseng Sa, who's now at Oak Ridge National Lab. Ali Snedden, who was my graduate student, is now working at a children's hospital doing medical research, and on the side does astrophysics. And Xinghai Zhao, who was Grant's graduate student, who now works at Dalton State College, and who is at really an institution where he does a lot of teaching. So we're finding ways for him to do research during the summer, and that part of that is kind of bringing him into the team. I mention that because I've been told that there's postdocs and some graduate students in the audience, and it's sometimes interesting to hear different ways of building your group and different ways to manage to do astrophysics as you move on in your career. A lot of the work you're going to see today has to do with is the product of my graduate students, including 2 current graduate students, Miguel Correa, who's close to finishing, and Gabao Tang, who is kind of midway after. Okay, so I said along the way we kind of got all of these tools together, and now we're doing something that's slightly different. So we were looking at the core cusp problem from a perspective of different cosmologies. You can also, so the core cusp problem is that discrepancy between the lambda CDM halo shapes of halos, particularly in smaller galaxies, and what you see observationally. Okay, and so we were tackling it using a different dark matter scenario, but you can find astrophysical ways of solving that problem. We have been looking forever at how different environments affect the evolution of the intergalactic medium. Well, not forever, I haven't lived forever, but it feels like since I was born, started working on that. And what is a galaxy's journey through the universe has been a question in our group. More recently, we've brought all our tools together to start answering how do different environments affect the evolution of the circumgalactic medium, the material around a galaxy, and the embedded galaxy. And this should probably have been around there. A side project which is going to become relevant to this is the observational signature of the dark energy equation, in particular of the yes, so the observational signature. You'll see we've done one project, but it's allowed us to develop code that allows us to probe different models of dark energy. And as you see here, we've around these questions, particularly the ones having to do with different types of structure, underpinning all of that, we've had this algorithm that is now, we've now used it for close to 20 years in different ways, but it's thinking about structure, and this is one way of thinking about structure, an algorithm taken from computer vision, but you'll recognize it when I talk about it as something that's pretty common now, pretty widespread in our field. There you go. Okay, so along the way, I've mostly studied in my whole career spectacularly modest environments. So there are the environments that people at first say, we can't see anything about these, so we're not going to even think about them. Density, so they're not clusters. This is a cluster, see infall, right? So the type of structures I've been interested in are voids that empty out, small dwarf galaxies, filaments, a lot of filaments. And in particular, what I've been interested in is not just thinking of them as a static structure, but thinking about them as a dynamic structure, and therefore getting to the idea of how cosmology impacts these structures, all the way to how galaxies experience these different environments in the cosmic web. So voids and filaments. For those of you who are graduate students, when I teach galaxies, I don't teach galactic dynamics. I have to remember that and not just do any training. But anyway, when I teach galaxies, one of the first things I want my students to remember is that although we see galaxies in pictures and photometry and the like, we look at a spectrum and we see some motion, but to always think of a galaxy as a snapshot of something that is in constant motion, right? It's orbits, it's an assembly of orbits, and what we see is kind of a statistical representation, a snapshot that tells us where things are more likely to be while they're orbiting everything. Well, in a way, you can think of the cosmic web in the same way. It is not a static object, although I'm not telling you that cluster is going to dance around the universe, so its location may be static, pretty much, but its components, what it's made of, is in constant motion. And so, while thinking about a galaxy in those structures, you really want to think about it's not staying put. You know, at the very most, maybe a galaxy right in the middle of a void would be the closest to a static thing you could think of in a static galaxy in the cosmic web. But otherwise, you have things streaming down filaments, entering clusters, doing their, orbiting within clusters. And it's important to keep that in mind. Okay, so what was my motivation for this work? Well, years ago, decades, I said, when I looked like this, I spent a summer here. Now, I was about to go to grad school. I had just finished honors physics with a minor in math at McGill, and I will freely admit that my brain was a bit fried. However, that summer, I started attending, for the first time in my life, theoretical astrophysics seminars. because I'd been at McGill where they didn't even have astrophysics at that time. I'd been at the Dominion of DAO, astrophysical, yeah, astronomical, not astrophysical. Yes, that's where astronomical observatory, where it was a lot of observational talks that I was able to go to, but I hadn't started looking at that. And so this was really an awakening of my theoretical astrophysics brain. And in particular, somewhere in my stuff, I still have a red-covered preprint of this paper. Now, for those of you who are younger, most of you are younger than me, a preprint was in the days where we didn't have archives. When something was ready for print, authors would get preprints they could distribute ahead of the time of this article showing up. And I remember reading this paper with absolute love, really. It was just falling in love with the cosmic light. Okay, so that's back then. I also met my advisor to be, Jerry Ostrecker, here at CITA when he came to give a talk, probably that same summer, because that's when I was here. And I went on to study the warm, hot intergalactic medium. Okay, so that was the origin story. Now, what are the more contemporary motivations? Well, this is not so contemporary, 1980, that's actually pre my coming to CITA, but this is a very, should be a very familiar diagram if you've studied galaxies, and it has to do with the morphology of galaxies in different environments. Here, just to remind you, you have emptier regions all the way to more dense regions, and not, for those of you who know this diagram, you'll know that you find fewer ellipticals in emptier regions, often in older papers called field regions, right? The field versus clusters. Is everything okay? It's moving along? Okay. And then you have more, the emptier regions or field regions are populated more with spirals. So this indicates that there is some potential morphological transition as you go from the emptier regions to the more dense regions. We also now getting to more contemporary, we've known for a while now that galaxies falling into clusters appear to be losing some of their gas. All right, so this is the Van Gorkum 2004, where you're seeing a galaxy falling in, and you see the galaxy and its gas displaced from one another, right? So it appears that the gas, as the galaxy approaches the denser environment, that galaxy is losing some of its materials. So same thing here. So that morphological transition is of interest, and it has to do with the type of structure you're in. Some of these contributing factors are going to be found more in denser environments. So galaxy harassment, galactic cannibalism, ram pressure stripping, of course, will depend on where you are, and quenching, which depends often on a transition. And these morphological effects exhibit some redshift dependence. Okay, so that's for that. That's the kind of more kind of emptier to more filled environment. Then if you go into the filamentary and wall network, so here's where I tell people who don't deal in filaments to beware when you're reading a paper on filaments. Filaments in our field take on very different scales. So they can be anything from kind of a filament of accretion onto a galaxy, or all the way to a filament that has multiple galaxies in it. The types of filaments I'm talking about are the ones that incorporate multiple galaxies and that span large regions of our universe. Okay, so when you go and look at filaments, galaxies in filaments, I just want to make sure I'm saying everything. Yes. All right, so when you go and look at filaments and galaxies and filaments, both in observations and in simulations, you tend to find some environmentally dependent effects, particularly in filaments. So, right, numerical simulations indicate that environment and temporal, so both the time that there's an environmental and temporal dependence on the spin orientation of the dark matter halo. So the spin of the dark matter halo will anti-align with the long axis of filaments. Okay, so we see that in dark matter in simulations, but it's and also there seems to be a mass dependence on this with halos with masses that are less than 10 to the 12 solar masses tend to have their spin vectors oriented parallel to the filament or more parallel, and more massive halos tend to have that anti-alignment that I just mentioned. So this is a good moment to think about, right, I'll get to the observational evidence first before I come to my conclusion. Yeah, so there's also observational evidence of this effect, but obviously not in the dark matter halo spin, but in the galaxy spin vector orientation, right? So this is the Navarro et al. So you have anti-alignment to alignment depending on mass in simulations, and you have in observation, you're seeing a similar effect, but with the visible matter, not surprisingly, right? You're not necessarily, you're not following the spin of the dark matter particles. Okay, so it's been suggested that tidal forces on galaxies within filaments can lead to a tendency for the angular momentum vectors of galaxies to be preferentially torque perpendicular to the axis of the filament. And that's going to have an impact on accretion and therefore on the star formation in those galaxies. Did you have a question?
No, not really. I mean, the only thing that I didn't understand is like, you are saying if one galaxy applies a torque on a different galaxy such that its spin vector is somewhat different.
No, I don't think it's galaxies. I don't think the argument is galaxies, because this is happening not just, so that's been suggested. It has been suggested, but I'm about to say what I think.
Okay.
So I just wanted to talk about hints that this may be important, but I don't think it's galaxies. I don't think it's one galaxy on the other. What we have, again, thinking of structure not as a static thing, but as a thing that is forming as the galaxies themselves form. You are now, when you're dealing with a filament, you're dealing with a very different environment than a cluster, for example, or a group, because it's much more directional. You have a direction of flow and you have a direction of infall for the material that are perpendicular to each other. In a way, you could imagine a cluster where you have some, infall this way, and it is, but you're dealing a lot more with that directional input. And I think that's what was hinted at in that paper. Yeah, so that's a good question. Yes?
So you consider structures of different masses. I've never heard this described, but must be investigated. How does the rotation depend on the mass? So you don't see strong rotational features in galaxy clusters as I recall. But they have to be rotating at some level. Groups have to be rotating at some level.
Right.
And are there systematics? You just consider this as mass.
So you're talking about at the cluster and group level, right? How so?
Function of, or even for dwarf galaxies, actually. I guess their tidal effects are like really, really strong.
Right. Yeah, so that's an interesting question. So I don't know that I have quite the answer right while I'm giving my talk, but I think I'll think about it a little bit more and maybe come back to it at the end. But I do want to mention that tidal effects are not necessarily going to be intuitive when you're dealing with the outskirts of clusters and with the infall of a galaxy into a cluster. You're going to find, for example, I was just talking, I'm going to forget the paper, but it's part of the group of papers that have 300 clusters simulations. One of them talked about the infall of a group into a cluster and what happens to it. And it's actually, at first, counterintuitive in that the more massive the group, the more shredded it is. And the less massive, the more it survives. So I think that that's not the work that I'm doing yet, but looking at those interactions within different types of structures is where we're going.
I guess just to say that the amplitude of density perturbation is obviously also relevant. So if you have a higher signal of perturbation,
yeah,
which is of course what we produce in our cluster, then there's less stuff of comparable mass around it to torque it.
Yes.
So my intuition would be that its angular momentum would be proportionally small.
Mm.
And is there, must be evidence for that.
There might. I do not know of evidence for it off the top of my head.
Sorry to interrupt.
No, that's good. I just don't know. I don't have that evidence off the top of my head, but I think it would. I see what you mean. Yeah, I see what you mean. Let me just check what to say. Oh yeah, we're good. Okay. Another motivator to take a second look at the influence, particularly of this filamentary structure on galaxies and their evolution, is that we're starting to find that and to be able to probe that environment with filaments being detected in Lyman alpha emission. And here it's Bacon et al. Using Muse. And essentially, after looking for overdensities of Lyman alpha emitters in the Hubble field. And so they extracted the diffuse emission surrounding the location of these emitters. So they did kind of a lot of the game right now of finding that diffuse emission has to do with differentiating the signal that you have from the more diffuse emission from known sources that you can extract. The second example that I'm going to use is exactly the same thing, except in the thermal Sunyaev-Sedlovish effect, in which you're looking at pairs of galaxies. And then again, so remember I told you about the different scales of filaments. In this case, it's material between two pairs of galaxies on a smaller scale than I typically deal with. But in this case, it's looking at two pairs of galaxies, stacking them up, subtracting the halos you expect from those galaxies, and then looking for an extra residual signal. And that was done by two different groups. I don't show all of the similar figures, but it's a similar analysis in this case. And they do find a residual between pairs of galaxies. So we're starting to have ways of characterizing it. I like to talk about local experts, so in a moment I will. But you know, there's obviously down the road there were some people who were looking at stacks. Again, this is stacking pairs of galaxies, so you're not just looking at one pair, but you're stacking pairs of galaxies and looking for residual signal. And you're going to have that proportional signal to the density in this case. So it's a good way to do it, but again, your densities are much, much, much lower than the sources you're extracting, right? The signal will therefore be much lower. Okay, so I did mention local experts. So this is a 2022 paper that was on the list of CITA papers. And this is a paper in anticipation of better observations that will allow us to start kind of moving away from the clusters, which we've been very good at finding in the Sunyaev-Zeldovich effect, to the more less dense regions around it, and at that interface, which is going to be a very interesting interface because of that transition that occurs between what's happening in the filaments, what happens in the filament versus what happens as you're transitioning from the filament to the cluster. So this is a really good paper. This is a good moment to give a disclaimer and to mention that actually I am citing some of local experts, but when I cite a local expert, it is not because I'm an expert in their work. So it's more to invite a conversation, and also to say, I've read their paper once, I need 3 times before I really assimilate somebody's paper. So happy to have conversations. And also, if there are any papers I missed, now's a good time to let me know about them and to talk to me about them, because we're writing the paper. And so you can be cited in that way. Right. So really good. Well, one last detail here. We see the underlying dark matter density in the simulation, and the gas density and the gas temperature. And what you're seeing is that the thermal Sunyaev-Zeldovich effect is really nicely probing the kind of fluffier structure that it is, and that's not me saying it, that's the paper saying it, but I can see that indeed that is the case. So a really good kind of probe of that.
There's Martine commenting for you.
Oh, the citation, great. Hello everyone online. Yeah, and then I was talking about that transition that, again, down the road, people you might want to talk about at Waterloo, talk to at Waterloo, but what happens to a galaxy when it transitions from one medium to the other? We've looked a little bit at that on the smaller scale. On the larger scale, going from a filament to into a cluster, what you're seeing is that you see a significant amount of quenching. So these diagrams are looking at fraction of quenched galaxies as a function of stellar mass, with the dotted red line at redshift of 0, and that dark line at infall, so first infall, and then there is so this is also looking at galaxies that would go into a cluster and might even come back out before coming back in. And you just see that the number now of quenched galaxies has risen. Oh, I should also mention that they're backscattered. They're different types of galaxies. So they're ancient infall galaxies over there, which makes sense that you have quite a bit of a difference between initial and now. And then you have infall now, recent infall, where you see almost no difference. And then you have, these are backscattered galaxies. Same schematic for this plot, but what you're looking at in this case is the fraction of hot gas. And I want you to direct your eye again to that kind of at infall and now plot lines. So the dark line at infall, red now, and you see that in fact you are really getting rid of a lot of hot gas. So quenching is occurring and you are getting rid of gas as well. Okay, now what we looked at recently was we were looking at the disk of galaxies. Again, one of those projects that our team just has interests and we go for them using the tools that we have. And so we were looking at a Milky Way-like galaxy. And this is work spearheaded by Xinhai Zhao. We were looking at the satellites of a Milky Way-like galaxy, and in particular the disk of satellites and how it may have formed. Now, I'm not going to go through all of the details of this paper, mostly because I want to go on and get to when I bring everything together. But it is a motivation for what we're looking at because we found that, in fact, so the big conclusion that we found was that we didn't have an isotropic distribution of dark matter subhalos that were just being kind of picked off in a disk-like formation, that in fact, not that surprising for me, but anyway, it was important to conclude that we were looking at a flattened distribution of dark matter halos. And importantly for what I'm using this for, that it seemed to indicate, if you followed that through time, so you're going from redshift of 5 to redshift of 0 now, that you could actually see some significant infall along a filament. So even the distribution of satellites around a Milky Way-like galaxy could be the result of that, at some point, some filamentary accretion. Now, those words, at some point, I'll also justify in a moment with work that we did. Okay, great. Okay, with a little detour through this nice image, that's courtesy of Descoteaux. So, long time ago, we started adapting an algorithm that detected vasculature in the brain for obvious reasons, because of our love of filaments, and looking at this, we were like, well, this makes sense to use on filamentary structure in our universe. And we started adapting it. This is something that a lot of people are now in that game of characterizing structure. If you need to use a structure finder, there are some publicly available, quite a lot of publicly available ones. In some cases, I do advise you to work with the first authors because, AstroCode is very different than professional code sometimes. I'm not saying that my code is like that too, but my brother programs for a living, so I know the difference. So in some cases, you might want to collaborate with, and in some cases, it will run fast. So don't always assume that you're getting it wrong if you're trying it and it's not working. Do get in touch with the authors. Okay, so what do these different, there are some topology-based algorithms. They tend to create a skeleton of the structure. You'll kind of have a through line of your structure and figure out where you have a transition from one type of structure to the other. You have, ours is a Hessian-based but multi-scaled algorithm that tends to not tell you where the center line is, but tell you the extent of your type of structure and whether your structure is more like something that's elongated or more like something that is clumpier. And ours has also developed so that we look at filaments. Some of these are more for particle-based simulations. Some are more for Eulerian or grid-based simulations. Ours does both, but I just wanted to situate ours. So it compares well with the others. But here's what I always say to my graduate students. They might say ad nauseum, but you want to figure out what question you're asking and what you need for it, right? And so things like disperse, we're actually going to use their results in a moment because that was more useful for the thing you wanted to. That's a topological, skeleton-based structure finder. And so with large-scale simulations, as with structure finders, figure out what you're using it for. Also, particularly for those of you who might be interested in void research, and in fact in all, the main thing you're going to have to think through are your boundaries between different structures. So where do you end one type of structure and where do you start another? A very easy exercise you can do in your brain is to think of a void, right? A void goes from an emptier space to a denser and denser space. And so you have to figure out when you're okay with this being the end of the void, right? And you may have just a density-based argument. shape of the density, but you might also have a physical argument by looking at the velocities and the like, looking at the behavior of material at your outskirts, right? But that's going to be your trickier region to define. We're pretty good at being, this place is empty. This place is long in one direction and short in two others. This place is very dense. We're very good at that, but the transition between those are a little trickier. Okay, so if you apply this was, I think, actually on a simulation by Remy Chen a long time ago, 2006 simulation, 92 megaparsecs, a long time ago. But if you apply it, you can find sheets using that Hessian base matrix. So you're using the second order information of your density and using the eigenvalues to figure out that something is long in one direction, short in two, long in two directions, short in one, approximately the same in three, and then you figure out a way to do your voids, which are basically anti-clusters. Okay, so you sheets, filaments, groups, and clusters, and so a long time ago we worked on that, and then we of course wanted to ask our own questions and started running Gadget 2 code. So we have the ability to run Gadget 2. We are working on updating it to Gadget 3 and 4. We haven't yet, but we have, on that, we've added a lot of baryonic physics that allows us to look at the intergalactic medium and the circumgalactic medium and think a little bit about how it's enriched over time and as a function of where it is. We've also since then worked with parametrized dark energy. We're working on at least one of my graduate students is working on fuzzy dark matter, and I'll tell you about self-interacting dark matter. But basically we have this capability, which I'll summarize in a moment. Right, baryonic physics, important. This is again, local expert, a paper taken from that list. That indicates that if you don't take into account baryonic physics while looking at structures, you're going to have the biggest discrepancy in the masses that you find in those different structures. In the volume fraction, it's not going to make as big of an impact. But if you think about, for example, tidal stripping and all of the different effects that you're interested in when you're doing galaxy evolution, those are going to be, it's what mass is where is going to make a difference, as opposed to what volume necessarily. So something to consider. All right, so using those simulations that Ali Sneddon did for his thesis, we looked at the intergalactic medium. I'm not going to go through the whole paper here, just highlight what's important for what I'm talking about today, which is that when you parse the intergalactic medium into different types of structures, clusters, filaments, emptier regions, voids, and note the unassigned regions, boundary regions that are hard to define, then you find that in fact, although you can tell a story about cluster gas in having some a more populated and a less diffuse gas and hotter gas, our filamentary network is going to be quite multi-phase. All right, so, and this is at redshift of 3.2, and then we look at higher redshifts. So you see that the distribution of gas in clusters, you get more towards the hot halo, and then in filaments, it's really all over the place. In voids, not surprisingly, you're going to have lower temperature, lower density, but lower density that may also be falling onto structures, again, leading to higher temperatures. Okay? So again, those boundaries are going to be a question. And the reason that I bring that up, I think I'll mention it while we're doing this, while I have this here. The reason I bring this up is let's think about what I'm interested in, right? What my group is interested in. We're interested in what a galaxy encounters as it evolves, right? If you sit on a galaxy and you think about where it's going and what it's encountering as it goes through and what you care about for its evolution, right? You're going to care about places where you change in density, places where you can accrete matter, places where you interact with another galaxy, right? So if your filaments are twisty and windy and multi-phase, then you can't just ignore all of the physical phenomena you thought, okay, I can relegate those to the cluster region. You can't ignore them for that. You also can't ignore them because a lot of galaxies are going to spend a lot of time in filaments, right? You're not going to have most of your galaxies in clusters. So both a temporal reason, a multi-phase reason to take a second look at that. The other thing to consider is that if I become super invested in this idea of directionality, of what direction your material is accreting, and therefore how it's going to accrete eventually onto the galaxy, these places also sometimes change. So what you're seeing here are little groups, and they're streaming towards a cluster-like region. But at some point, this is work that was done by Joe Zepeda, OMC. This is the second talk I give where his name is cropped out. Joe Zepeda, who didn't end up doing his thesis with me, but who worked for a summer with me, then came to graduate school at Notre Dame and has now graduated. He also taught a class in prison with me. So a really good graduate student. At the time he was an undergrad. And what we find is that there'll be some times where you re-engage that directionality if you have too much info. And so again, if you're thinking about where your material is coming from and what your galaxy is encountering, there may be times when you're thinking, oh, it's just falling onto a cluster, when in fact what it's encountering is very much like a dense filament. And why it matters is that you're going to have different gas dynamics, different dynamics of the gas with respect to its one. Okay, how much time do I have left? I'm almost done.
10, 12 minutes.
Oh, really? Great. That's better than I thought. Okay, let's go back there. All right. So I did mention that there are other types of structure finders. We are exploring a couple other types, including bringing some of our structure understanding to using machine learning. So Insang Sa is in charge of that, and Ali Snedden is looking at the topological nature. I did mention that he works at a hospital doing, basically being the high performance computing backbone of medical research at that children's hospital. And so he encounters different algorithms and has fun thinking about, can this bring anything new? This one may not bring anything new compared with disperse, although he's talking to a mathematician to make sure. So our group continues to evolve where it comes to structure finders. We have developed a dark matter only simulation that has a parametrization, the Linder-Chevalier-Polarski parametrization of dark energy in it. And we used it to look at the Lyman alpha forest power spectrum, but for our purposes, it will help us with departures from lambda CDM cosmology. Right, that was not supposed to be there. That's not what I'm talking about. And motivated by, this is a figure courtesy of Guan Nguyen, who's in my group, got it from Max Techlark. But looking at the discrepancy in density fluctuations at small scales and large scales of lambda CDM from what's been found, and that has that initially motivated. So this is what I should have shown. This initially motivated our own dark matter simulations with a particular cross-section that was larger than some of the ones that were in the literature. So we have that capability we're not really pushing the core cusp solution anymore, but it just allowed us to get there. And so Lan Nguyen is now our dark matter expert. Oh, okay, good. Down the road again, somebody staying at the perimeter. Two of the authors are staying at the perimeter. Really good white paper on the different forms of dark matter, and really thoughtful about how to go about probing these different scenarios. But the different scenarios that we're going to be looking at are, of course, cold dark matter, which is collisionless, collisionless and hierarchical in the way that it forms structures. And then we have looked at self-interacting dark matter, which has a collision cross-section, weak collision interaction cross-section, and potentially at fuzzy dark matter, depending on how fast my graduate student graduates. Okay, all that brings us to this. This was our framework for our research framework, where we had a whole bunch of types of simulations, both particle-based, Lagrangian, and grid-based, Eulerian. They each had their pluses and minuses when you're particularly interested in baryonic physics, which I've been a lot. And some are with baryonic physics, some have a population of baryons afterwards. If you're trying to follow along what's going on, the paper is at the end, and these indicate what we used to get to that paper, right? So this is why we have all these tools, is that we needed all these permutations for the different questions that we were asking. Now, one thing that we've added since that original is that we want now and going forward to have as our fiducial simulation whatever super large simulation is available of lambda CDM. Right now it's illustrious TNG, so that's what we're using, but we plan on having all our tools be able to be applied to that, because our idea is we look in these simulations, but then we can probe departures from lambda CDM cosmologies using this as our fiducial, making sure that we have that kind of touchstone, and then we get to depart from those from that lambda CDM cosmology. Well, that's just an illustrious. I should have been talking about illustrious with this in the background because it's prettier. But there's not actually something I was going to say that's other than illustrious, and please go and look at their papers. But for what I'm about to talk about, these are kind of more recent results that also will start talking about the impact of neighborhood, in particular that filamentary environment. Okay, so this is recent work by Miguel Pereira, and this is using illustrious TNG 100, so that publicly available large, scale, you still have to say what you're going to do with it, but large scale simulation. Here we're looking at the density right around the galaxy, out where you expect the circumgalactic medium to be, and then the density around that, which is the intergalactic medium. This is preliminary work, so that those definitions may actually change. They're just to, let's look at it now. This is the dispersed, right? Yeah, disperse. The distance to a minimum is the distance to a void. So that's in green. In blue, you have distance to a node, cluster, or group. And in orange, distance to a filament or the skeletal structure. And this is what you would expect, right? So you're going from higher redshift to now. So what are you seeing? You're seeing something that's going through probably a low density region, but that is accreting matter more or less over time into its circumgalactic medium. It seems to be close or in a filament, right? And that's great. Okay, so why would we even look at that? Well, because of this. You have the same thing, probably in a filament. And then you have this behavior where sometimes the density is much higher than others. Any clues as to what may be going on for the density to pop up and then to pop back down in the circumgalactic medium?
Merger or a big feedback event.
Yes, exactly. We think a merger, but again, you want to kind of keep track of those things. Probably a merger, yes. Or a big feedback event. Doesn't seem to be going through a denser region of the intergalactic medium. That doesn't seem to be what the case is. But that's why you want to track mergers, you want to track all of those different potential morphology impactors as you go through simulations. Okay, so this is why Keith is on our team. So I asked to stack Milky Way sized halos and look at the density of the intergalactic medium. So these increase in mass here, but it is not proportional. So they're just numbered here. Redshift over here again, and then you have the density it encounters as it goes through. Okay, so it also looks like a bloodbath. So my apologies for your eyes. It's going to get worse. So here, bear in mind that things that are really pale are higher density, things that are less pale are lower density. And then you have what's happening in the dense circumgalactic medium. There's a trend here that we're going to have to look at a little bit. It seems like you're actually getting a denser circumgalactic medium, and this was perplexing, why the lower mass halos seem to be accumulating more circumgalactic medium. I'm not sure that this trend will continue. But the reason we wanted to...
These are isolated things, not in clusters.
Yes, exactly.
And the measuring it out to the Imperial radius or something.
Yes, you're correct. So a very preliminary definition of what we're doing. So this is the circumgalactic medium. Correct, but that's our first stab at it. To really think about whether this was worth it or not. And so we're talking about things that are not in clusters, but that are periodically, sometimes multiple times, encountering denser regions. Okay? And this is a first crack at things. So I asked my graduate student, please use a different color scheme. And this is what I had. Now, the story would be better if I just called Keith right then and there, but I didn't. I had already talked to him about joining our team, but it will be useful. They're in talks, and the actual published version of this will not shock the eyes as much. Now the denser regions are in red. You're dealing with, again, the same information. And so you have perplexingly things that are going toward, that end up in less dense regions. CGM, end up with less CGM. I'm not sure. Again, the story of the game, I believe, will be what exactly was happening to these halos as this happened. All right, and this is the IGN. Again, mostly boring, except that you are finding that there are, in that non-uniform multi-phase medium, you are going through regions that are higher density, and therefore that could lead to different phenomena. Okay, right. So far, I've justified why we're looking at the environment of galaxies. I've noticed that I've mentioned that we have found that it has impacted different structures and different around galaxies, including disk of satellites. We have found that even structures as big as clusters can temporarily look nearby as a filament. So that what's important in that is that the galaxy itself might experience that as a very directional flow as it flows towards the cluster. We've mentioned that environment that a galaxy goes through is dynamic, and that it is multi-phase, particularly in the filamentary structure. And so dismissing the filamentary structure and only looking at the cluster regions, you might miss a good chunk of the story of galactic evolution. That is not to dismiss clusters and their surroundings. They are being studied carefully with reason, right? Because you're having that big density transition that can give rise to all kinds of juicy physics. So definitely a place you want to study, but if you're looking just at the time that a galaxy spends in our universe, you also want to look at the filamentary network. We've set up the tools for that. We had a 6 months delay that was only recently resolved because we didn't have enough room on our high performance, not enough storage on our high performance computing. Finally found out that it was because they were trying to get the university to move to a different format. So it's resolved now. And so we expect that after an SF grant goes in, the next thing is the paper will come out, because it's all ready to go. Final kind of note, structure, we're a galaxy, so we expect galaxies to be impacted. So structure is impacted by cosmology, and other people have done terrific work with voids. This is work by Alice Pisani, who I had a great privilege of talking to a couple summers ago in Aspen. But we see that we can look at structure to kind of probe cosmology. Those voids that Alice Pisani uses to probe cosmology are emptying out into regions that I study, right? And so those are also going to be impacted by cosmology. And so even though we're not saying at this point that we're going to be using anything we do as a cosmological probe, that's not what we're saying. We are saying that the structures we are studying are impacted by cosmology, and those structures have an impact on galaxy evolution. And we also know that the particular structure finder we use has been successfully used with Sloan Digital Sky Survey to find filament. And so we think that this work will pay off when we have those larger galaxy surveys, in that we'll be able to use the work we've done to look at those surveys. Right, that's it for now. Thank you very much.
So we are just past the hour, 100 minutes to run and go. Do we have any questions for Arielle? I had one thing I was interested in those history plots you just showed.
These.
Yeah.
Do you want green or red?
Either, I guess. I was
circumgalactic medium or intergalactic medium?
So kind of both. It's a common question about both of them. Mm-hmm. So the halo sample, is this are you tracing a halo that has a given sample mass?
Yes.
Redshift?
So we are looking at Milky Way sized. Yeah. That was again preliminary choice, but eventually we're looking at different sizes.
So should it just be moving horizontally?
Yes.
Or, so it's not taking into account accretion or decretion?
That's correct. Right now, again, that's just by number. Yeah. As I said, that's the mass stacked up, higher mass halos at the top, lower mass at the bottom, and you're just supposed to read it across. Yes, indeed.
I need to think more about what's going on. Martine has a question online.
Yes.
Hi.
Hi.
That's very quiet.
It's very
not
quiet.
Martine to say. Okay.
Is it better?
Yes. Hello.
Okay. Hi. How are you?
Hi. I'm guessing you're there.
So I was wondering about just the last little bit that you mentioned in terms of cosmology.
Yes.
Are you planning any studies in terms of like using simulations with varied cosmology, or Are there?
Yes, I'm sorry if that wasn't clear. That's the whole point of what I'm doing. So yes, absolutely. So we've set it up so that we can probe different dark energy scenarios and different dark scenarios and look at the impact both on the structures and on what happens to galaxies as they move through those different structures. So
Okay, great. Sorry, yeah.
looking out there.
I was thinking about in the context of the gas physics, but yeah.
You mean the
now I recall you mentioned.
Yes, absolutely. So when I say the structures, yes. So structures. Let me go back. Yes, that's part of it. So we want to look at the structures and how they are impacted, the intergalactic medium and how it's impacted, the circumgalactic medium and how it's impacted. And I actually have we're doing galaxy history of the environmental history of galaxies now. The paper is being done now, but actually we're simultaneously doing circumgalactic medium history. And it's how it evolves depending on the structure it's been in.
Okay, neat. Thanks. And that sort of brings me to, so my question is about, I guess, are you trying to probe like simultaneous variations in cosmology and in the gas dynamics by using the hydrodynamic sims, or like, do you have a kind of a plan or an idea of how to sort of marginalize over or deal with the degeneracies between those things? Because I know that's a
right. No, that's a very good question. This is why I was very careful to say this is not a cosmological probe, right? Because I had a lot of fun hanging out with people who are very carefully building cosmological probes. So we're not there yet. We're not there yet. We know that our galaxy evolution in our simulations is going to be impacted by the different dark matter scenarios we're looking at and dark energy parametrizations. Those are going to be done separately, but we're not at the level now where we could turn this into a cosmological probe. There's a lot of work that would need to be done to get there, if that's what you were asking.
Yeah, absolutely. Yeah, thanks.
Okay. yeah. But I'm aware of the work that needs to be done. I just need kind of another graduate student for that, because the ones I have will probably want to graduate before we get that done. But yeah, I think it has I have some ideas for things that could have promise and that would be complementary for what's out there that I did get while I was, those ideas kind of had their germination in Aspen when I was talking to people who were doing large scale structure cosmology. And therefore I know that we're not there yet. Yeah.
Okay, cool, thanks. Yeah, I'm thinking a lot of the same similar things. So I'd love to chat more if we.
Yeah, love to chat with you either through Zoom or in person.
Okay, thanks Martine, nice to see you. Anybody else have questions? I have a few more, but I'll ask them at desserts or something. So yeah, let's all thank Arielle again.
Thank you.